Hello everyone, good morning. I hope you are all fine. Today we are going to solve the last example for chapter 4, which is about the slab design, and we will also talk a little about the analysis of continuous systems, and I will give you a quick review about the analysis procedure that we talked about over the last sessions, and we will see how we can apply those ideas for the case of a slab analysis, and you will see how we are going to use it also in the project that we have for this course. If you have any question about the previous topics that we talked about, or if there is anything that we need to discuss more, don't hesitate to send me an email. We can definitely discuss this through email, or we can schedule a WebEx meeting and talk about the problem over there. So far, I believe I have talked to a great number of you, which is good. I really appreciate it. And I believe the office hours are providing good time for both of us to learn. I can see how you are following the course topics and how effectively I am giving you the materials. And you also have the time to ask me questions, and if there is any issue that was difficult to follow in the recorded files, we can discuss it over there and see the issue. So let's begin this chapter, this example, and see what we have to do for this problem. As you can see in this example, a continuous slab is given to us. As you can see in the plan portion that is given to us, we can see the slab, we can see 4 columns at the ends, and we can see 2 interior beams that are shown with dashed lines. Problem is asking us for designing the slab, and live load is given to us. Dead load is just slab self weight, and that is a very common situation. The slab is just resisting its own weight, and we might have some additional weights like for finishing or sealing of the lower level, and such things might be the additional dead loads on the slab, but usually the major dead load on slabs is the self weight of the slab. If you look at the project, that is very similar to real buildings, and as you can see, for the majority of the dead load that we have on the floor, we have the slab weight or the load per area just for the slab. Of course, over there I estimated the amount of slab thickness, and based on that I came up with the dead load, but once we design the slab, we will see that that will be the governing factor or governing parameter in terms of the dead loads that we have on the slab. So over here you can see live load is given to us, dead load is the slab self weight, and it is also telling us that the slab is not exposed to weather or in contact with ground. Largest aggregate size is mentioned as 1 inch, and the strength of materials that we are using over here in this problem are given here. F prime C is 4000 psi, and Fy is mentioned as grade 50 steel or 50,000 psi. So what I need to do at first is to understand the amount of demand that I have in this situation. So far, we learned that there are some analysis methods that we can use based on ACI code. And in this example, I didn't use them. I considered the slab as a simply supported system. And that's why you can see over here, I'm considering a simply supported beam. And based on that, I'm going to estimate the length and also the amount of demand or bending moment that I have on the slab. Let's see how we should analyze it like this, and then I will talk about the analysis procedure that we mentioned in the previous sessions, and we will see how we can use that in this situation. So we have this situation. the length that we should consider for the slab is the unsupported length, right? For example, at first I have to see how the load is distributed in the slab. We have the interior beams. We learned for the case of one-way slab, one side is much greater than the other side. Over here we have 15 feet. Over here we have 30 feet. So this side is about twice this side, which means we have a one-way slab. And the load is distributed in the short direction of the slab. So this is how the load is distributed over here. The load is going from the slab to the beams, and then from the beams, these interior beams, to the girders, and then from girders to the columns. So with that being said, I know this slab over here in this portion is acting or working like a beam. So this is the slab over there. The length is equal to 15 feet. This 15 feet slab portion is sitting between two beams, and then the load is applied on it, right? So that is the way I'm considering the slab. Usually in the problems that I give you as the exam or homework problem, I will mention, for example, you can consider it as a simply supported beam, or you can consider it as a continuous system. Considering this as a simply supported beam is more conservative in terms of designing the positive reinforcement over here, because this way the bending moment at the middle is greater than the situation of having continuous system. You can compare it, but let's say I want to use the method that we talked about at the end of chapter 4. I'm talking about this method, and see how I want to, or how can I use this method for finding the load on that slab. So this is the situation. If I want to show you the cross section of the situation, I have a column at the end like this, right? Then I have a beam. Then I have a beam. And then at the end I have another column, right? If I look from this side, this is what I see, right? We have a slab, we have interior beams, and then at the end we have the column. Right now we are looking at this portion of the slab, this portion. And if you look at this situation over here, we are talking about this situation, right? So the maximum moment in the middle of the slab is equal to 1/16 multiplied by WU ln squared, right? And then you can see the negative moment at the edges, minus 1/11. Those are the negative moments, and this is the positive moment. In our case, we are considering it as a simply supported beam, and we know the bending moment here is W L n squared over 8, right? So as you can see, the bending moment that we are estimating at the middle when we consider it as a simply supported system is much greater than what we had based on continuous systems. Of course, we will need to consider this situation for negative moment, but in this situation, I just wanted to consider it as a simply supported beam. And if I want you to use this continuous system and using the factors that I mentioned over here at the end of chapter 4, I will specify it. And for the project, you need to consider this. So the slab is located, or the load is distributed in this direction. That's why we considered the slab as a simply supported beam like this. This length is equal to 15 feet, and this is the loading on top of it. So now we are going to design this slab. For designing the slab, we know when we were talking about the slab design in chapter 4, we said there is some suggestions in the code suggesting us how to consider the slab thickness. If I want to show you that slide, I have to scroll up. And over here you can see in this part, in slide number 13, we said there is a table that tells us what is the suggested height or what is the minimum height for a slab when we want to design the slab, and also when we want to avoid any excessive deflection based on the situation that we have in the slab, whether it is both ends continuous or simply supported situation. It is suggesting us to use some value as the initial height of the slab. So I'm going to use this table, and this table is not something new to you. You have used a similar table for designing the beam, right? So we are going to use this table for designing the slab, and for the case of simply supported beams or simply supported slabs, we have L over 20, and I'm going to use that in this example over here. The minimum height for the slab section, I'm talking about the slab section over here, and the height that I'm going to consider it is L over 20, length is equal to 15 feet divided by 20. You can see the height is equal to 9 inches. So I'm going to take that as the height, and I'm not going to change it because for the slab we have not a great amount of load. Specifically in this case it just said self weight, so I know just by considering this section size I will have enough strength. Of course this is based on experience. Once you design this and you design the slab in the project, you will become more and more familiar with the slab design, and then based on that you can see that we are not really worried about the design of slabs, because just providing the minimum height and the minimum reinforcement will give us enough strength to carry regular loads. So minimum height is 9 inches, but the important thing over here when we are using this table is this condition. As you can see over here, it says that whenever you are using this table, you have to make sure your Fy is equal to 60 KSI, or your steel is grade 60. If the reinforcement or steel that you are using in your design is different than grade 60 steel, we have to update or modify these values based on a modifying factor. The factor is over here. So I'm going to modify the height that I got in my example based on that. As you can see, Fy that we have is equal to 50,000 PSI, and based on this I have to modify this factor, this height, based on this modifying or modification factor. So 9 is the thing that we got from the table. Now I have to modify it by this modification factor. This is 0.4 plus Fy over 100,000. 0.4 plus Fy, which is 50,000 over 100,000. And as you can see, this value is about 8 inches. So I'm going to pick 8 inches as the height of my slab section. This is the slab section, and the height is equal to 8 inches. Right? So this is our slab, and now I'm going to consider the rest or the other steps in the design. So far we could understand the height, right? If we were designing a beam right now, after finding the height we would start thinking about the width. But in this case we are designing a slab, and we know when we were talking about the slabs, we said we are going to assume the width of a slab are always 12 inches. Because we said a slab is actually a wide beam, but we are going to consider some separate stripes, some specific width in the slab, and based on that we consider the design section for the slab. We talked about it over here, as you can see, this is the discussion that we had during the presentation. You can go back and look at that to review that discussion. But whenever we are designing a slab, width is equal to 12 inches. Height is something that we found over here. And now this is the section, and we are going to add more details to this section. So B is equal to 12 inches based on the definition of a slab. Now we have to see how much cover we need to provide for this situation. For the cover, we have to use the same table that we used for beams. The only thing is that we just need to look at the part that was about the slabs. Over here, we are designing a slab. At first, I have to see the conditions. It says a slab is not exposed to weather or in contact with ground. So based on this, I have to see this situation, not exposed to weather in contact with ground. And now I'm designing a slab. So I have to look over here, and then for the first situation, it is number 14 to number 18 bars. And then the second situation is number 11 bars and smaller. For the slabs, it is very rare to reach these grade bars. It might happen for the case of very wide spans or extreme loads. But for the case of regular design and regular buildings, usually the smallest bars are going to help us, or number 4 or number 5 bars will usually get the job done. But commonly for the regular slabs, we are using small bars, and this will be the situation. So the amount of cover that I need to provide in the bottom of the section is equal to 3/4 or 3/4 inches. So that is the cover that I need to consider. That is shown over here. I know I'm going to have some reinforcement as the flexural reinforcement. I'm just putting the cover that the code specified in the lower region of the section. And now what I need to do is to see or design the reinforcement for steel in this section. For that, we had a table that we used for beams, but over here I'm going to just look at the code and see what is the suggested minimum of minimum reinforcement. You remember when we were designing beams, usually at the end of the analysis or design, we looked at that condition for AS minimum amount of reinforcement, and just checked if the reinforcement that we provided in the section is greater than the minimum or not. Because the amount of load on beams are much greater than the amount of load that we are looking at for slabs, the reinforcement that we need in the beams are much greater than the minimum reinforcement. For the case of a slab, based on my experience at least, we usually just need the minimum reinforcement, and sometimes even that much reinforcement gives us much greater strength than what we really need based on the load. So I always begin my slab design based on the minimum required reinforcement as the code suggests us over here. As you can see, it says a minimum area of flexural reinforcement AS mean is equal to 0.0018 AG, and this is about one-way slabs, the case that we are dealing with in the example problem. So the minimum reinforcement was 0.0018 multiplied by AG. This AG that we have is B multiplied by H. Putting that in the equation, 0.17 inches squared is the minimum reinforcement. If I look at that table that we had for number of bars, I mean the bar number, diameter, and cross-section area of the bars, I can see for number 3 bars, the area of number 3 is equal to 0.11. And I'm going to pick 5 number 3 bars. This is just a trial thing maybe I need to consider lower or higher than this based on what we get at the end. But one thing that I suggest you to always consider in your flexural reinforcement design, these tension reinforcement that we put in the bottom of the sections, is that it is better to have smaller and distributed bars instead of having very bulky and thick or large size reinforcement with small numbers. Like for example, over here I have 5 number 3 bars. You can say, hey, why don't you pick, for example, 1 number 6 bar or 1 number 5 bar? That is possible, but the thing is that when you have such a big reinforcement as your tensile reinforcement and just 1 or 2 bars in the section, it will create a huge amount of stress or interaction stress between the reinforcement and concrete. And this stress concentration will create lots of cracking and increases the chance of having separation between the reinforcement and concrete. For dealing with that issue, it is better to distribute the reinforcement with greater number of bars, or it is better to say with a larger number of bars. I'm talking about more bars in the section instead of having just a few bars. Having more bars and distributing the load between more bars in the section is better in terms of the stress distribution and a uniform work and a uniform load distribution between the reinforcement and concrete. Of course, in situations like this, when we are using a greater number of bars in the section, the issue that we might face will be about the spacing. Over here, you can see at the end, based on this situation, I can obtain the strength, I can satisfy all the conditions, but there is one issue that we will discuss at the end. But again, the thing that I want you to remember is to have more or greater number of bars, more bars in the section instead of just 1 or 2 bulky, large cross-section bars. Smaller bars, but with more bars in the section are better than just having 1 big bar, because that will cause a stress concentration. So design is always a trial procedure. Of course, I had my tries before preparing the files. You can try more at home. You can consider, for example, instead of 5 number 3 bars, 4 number 4 bars, or 3 number 5 bars. You know, I'm just talking about playing with the number and diameter to see what will be the result. Over here, I'm going to go with 5 number 3 bars. As you can see, the area that I have is greater than this, which is fine. That was just the minimum reinforcement that we have to provide. Being a bit higher than this is good. If I wanted to just look at this, I would go with only 2 number 3 bars. But again, this is just AS min, the minimum reinforcement that we need. It is fine to go a bit beyond that. So based on having 5 number 3 bars, now I need to check the spacing. The spacing that we have between bars is equal to 12 inches minus 5 diameter of the bars, because I have 5 bars, and then divided by 6 the spacing or the spaces that we have between these bars. And as you can see, these are 1, 2, 3, 4, 5, and 6. Please remember that we are designing a slab. This is not like a beam that these are the ends of the section. The section is actually continuous, and we are just considering this portion of the section or this portion of the slab as the cross section that we are designing. But the slab is actually a continuous section like this. So the spacing that we have in the section is over here. It is shown from face of one bar to the face of the other bar, and it is calculated over here. As you can see, this spacing is equal to 1.7 inches. Of course, it is a small value, but let's see if it is satisfying the minimum spacing that we need based on the code. The minimum spacing says max is equal to diameter of the bar 1 inches and 4/3 multiplied by diameter of aggregate. Diameter of the bar is equal to diameter of number 3 bars is equal to 0.375, 1 inch, and also 4/3 multiplied by diameter of aggregate, that was 1. So the governing value over here will be 4/3 or 1.33 inches. As you can see, it is the spacing that we have is greater than that, so that is good. If you look at the code, it is also suggesting us to consider a maximum spacing between the bars, and that is mentioned over here. And that is the smaller of 3H or 18 inches. That is the maximum spacing. So, the smaller of 3 multiplied by 8 or 3 multiplied by height or 18. Height is equal to 8. And the minimum of these two is equal to 18 inches. So that is the maximum spacing. And as you can see, this value is between the two. And we can say it is okay. In the examples that I solve for the beams and slabs, I always check the spacing based on the minimum requirement and maximum limit that we have from the code. There is also a third thing or a third condition that we need to consider, and I believe so far you have thought about it, and by now you know what is that third condition, right? There are the limits from the code, and there is a third condition that we have to always consider when we are designing real projects, and that is whether it is possible for the workers to construct our drawings or not. So right now, based on just looking at the codes and satisfying all the numbers on the papers, we have a good spacing, right? But is it possible for the workers outside, when they are constructing this section that we designed on the paper, is it easy for them to apply this spacing between the bars? This is something that we need to always have in mind. We will talk about it more at the end, but I just want you to always have this in mind. What we are putting on the paper is something that the workers should be able to really construct by just using a tape measure and very simple measurement tools. So the spacing that we have between the reinforcements so far is equal to 1.7 inches. And this is between the limits. So far we are in good shape in terms of the section conditions. So these are the final section information. Width is equal to 12 inches. 8 inches is the height. We have 3/4 inches the cover below the reinforcement, and I have 5 number 3 bars, and the spacing is mentioned over here. So now that I know the section, I can understand the dead load that I have on the slab. That dead load is based on the slab self-weight, and now that I know the geometry and the cross-section dimensions, I can estimate the dead load. That is 1/150 pound. So this is PCF, or pound per cubic foot. That is the typical weight per volume of reinforced concrete. So 1/50 multiplied by 8 inches and 12 inches will be the linear load or load per length of the slab. So 150 is pound per cubic foot. 8 inches and 12 inches should be transformed into foot. And then once we do that, I have to just change it to kip. That's why I'm dividing it by 1000. and at the end you can see dead load is equal to 0.1 kip per foot. The live load that we have is specified in the problem. Live load is equal to 200 pound per square foot. And what I need to do is to just multiply it by the width of the slab to find the live load on the slab per length. And that is 0.2 kip per foot. Now I have to just consider the load combinations that we had for gravity loads. We used it a lot before. You are familiar with it. We had two important load combinations for gravity loads, and those are specified over here. The first one is 1.4 dead. The other one is 1.2 dead plus 1.6 live. Putting these loads that we found earlier in these two load combinations, you can see the values, and the maximum of these two is the ultimate loading that I need to consider on my slab. That is 0.44 kip per foot. Having this, I can calculate the maximum moment, which is WU squared over A. W is equal to 0.44. L is equal to 15. The L is the length of the slab, 15. And this is the portion that we are designing right now. So that is length is equal to 15, and then calculating this, it is 12.4 kip per foot. Again, this is the maximum moment when we have a simply supported beam, and the maximum moment is happening always in the middle of the beam. Right? This is the equation that I'm using for the case of having a simply supported beam. If I were to use or if I were to continue to consider this as a continuous system, I would look at this graph. I would say, okay, I'm looking at the middle span, and based on this, the maximum moment is equal to 1/16 multiplied by, as you can see over here, WU ln squared. WU is the thing that we calculated, and then ln is the length of the slab. Of course, ln is the length from one face of the support to the other face, but in situations where, like in this example, where we don't know the length or the section size of the column and beams, we can just consider the center line length, or the distance from one center line to the other center line. So, returning to the situation, we found the maximum moment or the ultimate moment, and now I have to compare it versus phi mn. If phi mn is greater than this, then we are good. If not, the section should be modified. So I have to just analyze this section. The analysis procedure is something that we did several times before. You are familiar with it, considering the linear strain distribution, the stress distribution and forces, and then based on this, I need to just find the moment because of one force about the other. Tension force is equal to ASFY. We are always assuming steel at the bottom has yielded, and then we will check this assumption based on looking at the strain that we have, or at the strain at the level of reinforcement. So tension force is equal to ASFY. We have 5 number 3 bars. Area is equal to 0.55. Fy is equal to 50,000 psi, and based on that we can see tension force is equal to 27 kips or 27,500 pounds. This tension force is equal to the compression force at the top. The compression force is equal to 0.85 F prime C. That is the intensity of the stress multiplied by B, which is 12 inches, and then multiplied by A, which is depth of the compression block. A is the parameter that I don't know. So considering the equilibrium between these two forces, I can find A as 0.67 inches. Right? So I know A. Now I can look at the strain distribution and find C, or depth of neutral axis. And that is based on this famous equation that we used before. We know A is equal to beta 1C, so C will be just A divided by beta 1. F prime C over here is equal to 4000, and for this situation we know beta 1 is equal to 0.85. Putting that over here, C is equal to 0.79 inches, right? So I know C, which is this distance over here. All I need to do now is to calculate D, this total distance, and once I know that, I can use the ratios that we can define for these similar triangles. One is over here, the other one is at the top, and based on the ratios of sides in these similar triangles, I can find the epsilon T, or strain, at the level of reinforcement. So epsilon T over this side, which is D minus C, is equal to epsilon C over C. Epsilon C is equal to 0.003. That is the maximum strain for concrete based on the code suggestion. As you remember, in the very first presentation, we agreed on this value. So D is this distance. Total height of the section is 8 inches. I have 0.75 or 3/4 inches over here. I just need to add half of bore diameter to find the D, or this distance over here. So 8 minus 3/4, or 0.75, minus half of bore diameter, that will be this distance over here. And as you can see, that is 7 inches. So that is the D. Now put it in this equation. Epsilon T is equal to 0.025, much greater than the yield strain. And of course, it is greater than the yield plus 0.003. So the section is tension controlled, which is good. Phi is equal to 0.9. I have to just calculate the moment right now, and that is phi mn. So phi is 0.9, mn is tension force, multiplied by this distance, which is D minus A over T. Right? Considering that, the equation is over here, and multiplying these together, this is the value in pound and inch, dividing it by 12,000. You can see the moment that we got is 14 cube foot. Remember that when I was designing the section, I just picked the minimum height. Then for the reinforcement, I just calculate the minimum required reinforcement and went a little above it. And by doing those things, at the end of the day, I got 14 cube foot. The MU that we calculated based on a slab weight and some given live load was equal to 12.14. As you can see, the strength that we got is very close to that. So the section that we designed is good in terms of the strength, and it is also passing the requirements for spacing of reinforcement. The design is not done yet. If we were looking at the beam, just coming up with the geometry and designing the reinforcement and finding the strength would be all the things that we need to do. Over here, we are designing slabs. And as you remember from the very first chapter, we said one issue that we have for large concrete portions is great amount of shrinkage. Over here, we are designing a very large section like this. This is the slab section, and we have to take care of shrinkage for large sections like this. And for taking care of shrinkage, we need to add shrinkage reinforcement. As you remember in the discussion that we had for slab design, we talked about shrinkage reinforcement that should be over here. And as you can see, code is suggesting us to use shrinkage reinforcement, and the amount is just based on some spacing limit that code is suggesting us. I always consider this and it works. So just consider this when you are designing shrinkage reinforcement. Shrinkage reinforcement should not provide any strength. It is not there to give us any strength, so it does not really need any analysis. What I need to do is to just provide some reinforcement in a certain spacing condition to just have the shrinkage reinforcement in the slab. And as you can see, that the spacing is the smaller of 5H or 18. So having this, I can return to the question. It says the shrinkage reinforcement should be, the amount is based on this paragraph or this statement. It says the ratio of deformed shrinkage reinforcement is 0.0018. When it is talking about the ratio, it is talking about a shrinkage or the area for shrinkage reinforcement over BH. This should be greater than 0.0018. So that's how I usually just see the situation or find the reinforcement. Based on the code suggestion, the area of shrinkage reinforcement in the section should be greater than this. And as you can see, that is 0.17. So if I just use 2 number 3 bars, as you can see, I am providing that, and that is enough. I just need to provide that area for shrinkage reinforcement in the section. The minimum was this, so I just want to go a little above that. So 2 number 3 bars is going to deliver the requirement, and each number 3 bar has 0.11 inches squared area. So 2 of those will satisfy what the code requires. And then the spacing, I am going to just provide the spacing based on the maximum spacing that the code is suggesting us, and that is based on minimum of 18 and 5/8. 5 multiplied by height is equal to 8 inches, and based on that we know that the minimum is 18. So I'm going to say we have to have shrinkage reinforcement. I'm going to use 2 number 3 bars, and the spacing between the bars is equal to 18 inches. And also note that the shrinkage reinforcement, I'm showing that with red, that is in the transverse direction. It is not in the flexural direction or in the load distribution direction. It is in the transverse direction. That's why I showed the length of it instead of the cross section of it. If I want to show the cross section, I have to see the other side of the slab. The blue bars are the flexural reinforcement, and this red bar is the shrinkage reinforcement in the transverse direction. If I want to show you all of these reinforcement in the actual problem, these are the flexural reinforcement. We said at every 12 inches we have 5 number 3 bars, and the spacing was 1.7 inches. That's why these are very close. Of course, we are looking at the top, and over here this length that you are looking at is actually 30 feet. That's why 1.7 inches is this small, but these are the flexural reinforcement, and these should be in the whole length or in the whole portion of the slab. I just showed them in one section in 12 inches, but it should be in the whole slab, and these red bars are the shrinkage reinforcement, and as you can see, these are in the transverse direction. Load is distributed like this. That's why we have the flexural reinforcement in this direction and then the shrinkage reinforcement. As I told you earlier, and as you remember, I said there is a third condition when we are designing the reinforcement, specifically the spacing, and that is whether it is possible to construct it or not. So 1.7 inches as the spacing between the bars is satisfying all the limits based on the code, but yet it might not be very practical in terms of the constructability, or whether the workers that we have in the site can really construct the slab. At the end of the day, we should be able to pump the concrete, and it should go through the slab, and also workers should be able to really construct this slab and put the reinforcement in the site. So maybe for the second try, one thing that you can do is to just consider number 4 bars, and this time we can consider a larger spacing. Instead of 1.7, maybe we can have, for example, about 2 inches, and that would be easier for workers to construct. But that is something that is not in the code. That is highly based on your experience and the situation that we are dealing with in the construction. In terms of the requirements, just based on the theory and the code requirements, we could design the slab, and this is the final configuration. Again, you have the time at home, so I recommend you to design the slab again. And one thing that you can change is to, for example, instead of number 3 bars, which are the smallest bars, you can go with number 4 and number 5 and see what is the situation based on these bars. But for the case of shrinkage reinforcement, you can use the smallest bar, just use the same number 3 bars. You don't need to change that because the spacing is large enough for that. For the case of flexural reinforcement, you can play with the bar size. If you have any question, just send me your question and we can discuss that through email or WebEx. Thank you.